second level with the subcortical mask, so perhaps we can look at those results afterwards.
Fantastic. Yes, I'm interested in looking at that as well.
It doesn't really look that different to me.
Right. So I wanted to comment on those results as well, the subcortical stuff, because those are related to well, we'll get to that. So we'll talk about that later.
Is this the spherical?
So what I was doing. So I was doing subcortical analyses, but comparing two different methods. The first one was using spherical ROIs that I placed at the MNI 152 coordinates specified by the DIVA model. And for the spherical ROIs, I created two sets, so one with a radius of 4 millimeters and one with a radius of 6. And then the second type of ROI that I used was taken from 3 different probabilistic atlases that I've listed here. So there's a different atlas for the basal ganglia, the thalamus, as well as the cerebellum. So first, to go with the spherical ROI, so this is the total list.
If I just turn the light off in anticipation of that impact.
You sound optimistic that there's going to be something to see.
Oh.
No, I'm kidding. It's easier. It's easier to. So the first time I ran this, I put in every ROI just as an individual ROI, and then the second time I combined some of them, which I'll come back to in a second. And then looking at this for each contrast, so starting with speech minus baseline, and how these are going to be sequenced is I'll show you the 4 millimeters followed by the 6 for each contrast as we go through them. So for speech minus baseline, there are a lot of significant areas of activation, right
Just about all of them.
But pretty much all of them. And there's, they're pretty consistent between the 4 and the 6. Like there's some differences, a couple of extra areas show up, but generally like the pattern.
For the 6, there are a couple of extra areas.
So like if you look at
These spherical ROIs are all looking at subcortical structures, or what is it that we're looking at? Sorry.
Yeah, exactly. So these are for all of these structures, there's a spherical ROI placed at the DIVA model coordinate.
Okay, fantastic.
Is that the same thing when Frank says speech lab ROIs? Is that the same thing as DIVA ROIs?
No, so the speech lab ROIs is a parcellation scheme where you take the cortex and it's,
Just like that?
Yeah, you just cut out
You just cut out pieces
parcels, of the brain. And why it's different to other parcellation schemes is that it's divided in such a way that it isolates areas that are more critical for speech, whereas typically the areas are larger, and correct me if I'm saying anything wrong, if anything that you might wash out an effect, right? So
it's all of the brain's ROIs, it's just divided in an in-house way. It's our in-house recipes for the other brain, not whole brain. Whole brains worth of ROIs. Yeah. Versus a DIVA ROIs are just the ROIs that are active.
And the source, so the speech lab ROIs are based on cortical anatomy, where the DIVA ROIs are based on our previous studies and some meta-analyses that Frank ran, try to find like centroids, the localized components of the DIVA model. Mm-hmm. So they're when we in practice when we talk about them, they're defined in MNI space. Okay. Where the speech lab ROIs are defined according to sulci and gyri anatomical landmarks.
And these are all in MNI space, or some MNI coordinates, or are they subject specific in any way or something like that?
These are in MNI space.
MNI space.
So then I used your really nice con MNI create ROI function to create.
Excellent.
Yeah.
Perfect.
And actually, Matt, just on talking about the speech lab ROIs, on the lab website, there's a link to the ROIs with like I know they're in Frank's book as well, but it's just like a nice quick resource just to, there's like an image of the ROIs and then all of the acronyms.
Okay. Thank you.
And I think Jason is putting together more documentation.
I am, and
Coming
it's,
soon.
as we go, I don't know, we went so long without really doing a lot of ROI analysis, and now we're doing all the possible ones.
Yeah. Okay, so
And these are broken by hemisphere, so right and left for most of them? Or?
right, they are, but then when I ran them all together. I don't know if that was correct or not.
Oh yeah, that's perfectly fine, yeah.
So Jason, what I had said here was that for the 4 millimeter, see there's a couple of areas that if they don't have the black bar, they don't reach significance when under FGR correction. So then when at the 6 millimeter level, they all work, but it's really only 2 or 3 areas.
Hey, Elaine.
Yeah.
Were these run on unsmooth data or smooth data?
So this was all unsmooth data. So I went back and ran another processing. No, what did I do? Maybe it was at the first level. Yeah, it was at the first level. I set the smoothing to 0. So then there's like a separate first level analyses, and then I ran this on that.
Okay, awesome. Thanks.
I think when you're doing something like this, where it's defined in an atlas, the smoothing is probably the way to go. Right? I would say,
really?
Because if we're doing ROI analysis where we're defining, Alfonso, before I go on in this, do you agree with that?
Yeah, I agree. I mean, for spherical ROIs, the border of the sphere is not all that meaningful or representative. But you don't care if you smooth a little bit across that border.
You're just saying, you don't. I'll flip it. If you're defining on an individual subject, it's like you go in and you label the thalamus, and I labeled that subject's thalamus. In that case, you may not want to smooth. I mean, there still might be a little bit of reason to smooth, but you could just not smooth at that point because you're literally extracting those voxels from that subject in that area, and you're confident of that. Here, we don't know how they're going to align, so the smoothing actually probably helps with that.
Okay, that's good to know. Yeah, because I had just, in my head, I was like, oh, it's ROI analysis and it's smoothing, but when you explain it, it makes sense.
Yeah, if we're doing individual ROIs even when we do now, if we just automatically label the cortex for each individual, you probably still want to do some smoothing because we're not going in and correcting it and fixing it.
Yeah.
If you were using the free surfer subcortical ROIs, those are probably accurate enough that maybe you wouldn't want to smooth or smooth just a little bit.
Yeah. So yeah, go on.
Oh, what's an appropriate level of smoothing for this? So we run all of the pre-processing at a 4 millimeter and 8 millimeter smoothing level. Is 4 millimeters too smoothed? Not appropriately smoothed for this, or what do you think?
Right. I mean, there is no right answer here. It's the smoothing basically adds to the effective size of your ROI. So mathematically, it's equivalent to smooth the data and then look into a binary mask like what we are doing here, or look at the raw data and smooth the mask itself and get like a probabilistic mask instead of a binary mask. The two are totally equivalent. So in a way, what you're doing basically is blurring the boundaries a little bit of your 6 millimeter spherical ROIs by some amount, by the amount of the smoothing kernel. So you can imagine, I mean, the effect of different amount of smoothing. 6 millimeter is the radius or the diameter of these spherical ROIs here?
What was
radius?
It's radius, yeah.
Oh, so
It's the radius, so something like 12 millimeters. So if you're smoothing by something like 8 millimeter, full half, so that's effectively increasing by, I don't know, 50%, like this, the effective size of the ROI. So perhaps it might be too much, I don't know. But on the other hand, the 8 millimeter is kind of like the preferred value for correcting across. I mean, because smoothing is not only to increase the signal to noise ratio, is to correct for potential difference in the exact location of the thing that you care about across subjects. So I don't know, 12 millimeter ROI diameter is already relatively large, so probably 4 millimeter smoothing would be fine. But in general, 8 millimeter smoothing I like. So I don't know, it's really relatively. I don't think we will see a huge difference. In the larger the ROI, the less difference the smoothing is going to make in general, and the smaller the ROI, the more difference it's going to make. So I don't have a very good answer for this.
It seems like 6 millimeter ROI with radius, 6 millimeter radius ROI, 8 millimeters smoothing. I think that's kind of big, but you know it. So maybe 4 or 4 and 8, something like that. That might be something to play around with. I don't know if you have this. I think you had this at one point. I don't know if it's in the slide, but looking at how these things align with
Oh yeah, I don't have that. As in, it is. I have looked at it on preview. It's a bit, at least right now for me, it's a bit complex to visualize it in a nice figure, but still.
Right, and that's kind of like the point of what I wanted to discuss later about the issue with the masking that basically had to do with how well or badly the subcortical structures co-register after M&A normalization across subjects. And so we should look at that, take a look at that, basically just look at the structural data after normalization and the functional data after normalization and focus a little bit on subcortical structures to get a sense of how much variability, residual variability in the exact location of these regions that we care about, how much residual variability they have even after normalization. And that, I mean, it's all to help us better inform about what is the size of the regions that we should be focusing on, depending on the amount of the size of the actual regions that we care about compared to the size of the variability across subjects in the location of those regions. So we can do that basically later on. We look at the variability to see if we get a sense of how much variability there is. Because to me, it was a little bit larger than what I would expect, which basically justify why there are things that are focused specifically on like cerebral or like SUG for normalization of these structures, or perhaps we should be paying a little bit more attention to facial for parcellation. I don't know. We'll talk about this later.
Okay, that sounds good to come back to in a while. So then the next slide is a fast normal contrast with a 4 millimeter radius ROI, and none of these showed significant activation. I'm saying, oh no, sorry, then for the 6 millimeter though, we did get the right cerebellum lobe 5 speech node was significantly different.
And what is the other region that is kind of close to significant as well? The one that is like that probably shows significance at the uncorrected but not FDR correctly.
Right. Oh, right. So it's right thalamus. Yep.
That's interesting that actually does pop up.
Yeah, and I think that comes up later again in another contrast. Stress normal, here there wasn't anything, but I guess if we look at the, uncorrected, the green one is basal ganglia putamen in the right hemisphere. And that's similar as well for the 6 millimeter, as well as the left thalamus VL nucleus, so the ventrolateral. They're is normal. There's a few different ones that are near but not quite significant.
So it would be interesting to look at that. So we load up that medial geniculate ROI because the medial geniculate is very, very small. If the medial and lateral geniculate are not like packed into that ball of the thalamus that you usually see, it's kind of separate, kind of hanging off. But you can imagine if you put something centered there, you're going to get pallidum, you're going to get some flaming nucleus. You're going to get some stuff that has nothing to do with anything, maybe possibly hippocampus. So it is, now I'm kind of waffling a little bit. I'm like, don't on the whether or not we should not smooth. I mean, we should smooth some, but maybe the 4 millimeter smoothing, because these are actually fairly big.
Right.
8 millimeter, fairly big compared to what we were looking at.
Yeah.
That's the thing. So, I mean, ultimately, I think the way to do this is where we have so we have a way of labeling the cerebellum, the lobules. It's probably going to be better than just doing an MRI coordinate one. I'll hold that. We'll see it because we have that. Right? We have another coordinate based one.
Yeah.
And we have we have all those the putamen, pallidum, at that level. We have that for each individual subject. So I think the way to do this is for those that we have individual ROIs. Once we have that capability, that's the way to go. And then for these other ones where they're smaller, where we just don't have that, then we resort to using the subcomponents and just kind of hope that they pop up. It would be interesting, Alfonso, to come up with some way to use as an input to some system that is the FreeShare for ROIs, but then we go in and do something to try to. So we try to find the subcomponents once we have them, rather than just a straight up probabilistic analysis.
But what I'm not sure I understood what sort of transformations you're thinking about.
So what I'm thinking is if you come up with a probabilistic atlas within say a thalamus parcellation. So you label the thalamus, and then you localize the subcomponents within that individual thalamus location. That's not something we can just add. That would be a project. That would be maybe if we could get some data, from someone that's labeled a lot of thalamus.
Maybe not before these studies are
No,
published.
not before that.
On the wish list.
I see what you
Yeah, if you look at the kernel slice, it's the thalamus, medial geniculate there, minor geniculate there. So they're it would be it would be good to see.
This is clear, normal.
So fast mouse clear, there are a lot of negative activations.
Yeah.
That's interesting. And that's interesting.
Yeah, there's definitely a different pattern to say, stress minus normal compared to.
And that's what we thought there would be a lot of more activation in the clear with fast. Sorry with getting it right.
Yeah, they're kind of the speaking cells that are the opposite ends of the spectrum.
So GPE goes the other way, but it's kind of hard to interpret what that means because that's an inhibitory region. So it'd be more active.
Would be more
inhibitory of the cortex. But we, I don't know if it's straightforward to say that more whole means.
Right.
It's kind of hard to.
So I don't know if just looking at these, I know it's a pretty brief look, but if you have any thoughts on like 4 versus 6, or is it very structure dependent? Like.
Yeah, but something like the putamen or the whole thalamus or caudate, 6 seems, that's going to be a fairly small piece, right? You're trying to locate this area that across a bunch of studies seem to be more active during speech. So you want to localize it to some degree, but it's I think it would be good to do a sanity check and see, kind of just like, let's take a look at what these things look like. Because if we're trying to get, I don't know, I guess medial geniculate, that's probably Although there are subforms of the thalamus here.
Yeah.
Interesting to see just how big they are. And I suspect that they'll be overlapping for this one too. Right? Is that the case?
Most of them don't overlap actually, but they're some of them, at least for the 4 millimeter one, they tend not to. But some of them do. So then this was basically the same analysis again, but with combining some of the regions. So if the regions I've shown which ones are combined, and then if they weren't combined, the individual remaining ones were still just entered into the analysis. So the anterior putamen and putamen were combined, the ventral anterior and ventrolateral nuclei of the thalamus, as well as all of the cerebellar nodes as well. And then what we got. So again, very similar, clear activation in speech minus baseline for both the 4 and the 6. And it is, there's a parallel here with the regions that weren't active previously in the 4 millimeter, and in this analysis. So there's just a nice consistency between them, which is what we would expect. But, it's always nice to see that. Then fast comes normal. Stress minus normal. They're minus normal. And fast minus clear. So none of the speech contrast, reach significance. I know I've gone through that super quickly. I don't know if there's anything there you want to look at a bit more detail.
One thing that would be interesting to see is if you could just say, how could we test for there just being lower activation in the fast condition across the subcortical region, something like that. There's a way to do that now, but is there a way to do it? It's not cheating. I guess they're lower, but the variability is so high that probably still wouldn't see. The average across all of these is lower for fast than it is for, say, clear. But maybe on that level, that may be one way to just say it's a general reduction in the activation in certain structures.
Okay. Then the last set of analyses was using the probabilistic ROIs. So we have, based on the method or the atlas, or the 3 different atlases, these were all of the regions. So here we do have all of the cerebellar lobes differentiated, whereas before all of the cerebellar nodes were just in lobe 5, right?
5 and 6.
5 and 6 have all of the kind of more speech-related ones.
And these are, are these defined at the group level?
Yeah, so these are, again, MNI template.
Okay.
MNI space.
And do you have a plot by any chance of these regions just to see a little bit of what is the probability of a couple of those regions? I mean, how those probability kind of level off at the borders? I'm interested in just seeing
That's a good
how
question.
similar to a binary ROI they are or not.
Oh, right. So I should actually say that even though these were derived from probabilistic atlas, I was actually using the binary mask.
Oh, okay. So they are. So you were using the dot ROI instead of the dot WROI for these results, right? Okay. So that's effectively, I think, thresholding it by, I think it's 0.5, or perhaps 0. I'm not totally sure, so I will double check to see what is happening.
Before that step, I did I didn't put the whole atlas into the FL command. I think that's now available, but I don't think this was available a few days ago when I was first running it. So I use the rect split command to take that atlas and
to break it into
Yeah.
right. I mean, now if the atlas is like a 4D volume with a fourth dimension being the different ROIs and the actual values being the p-values, you should be able to just run it as a single file using the WROIs option to get weighted, well, those weights basically in a more, well, taking into account when doing these computations.
Yeah. So maybe I can try that.
And when you show the results, those are corrected for the number of ROIs.
Yeah.
Right? So in this one, so for cerebellum,
Yeah.
for low 1 through 4, probably we could just
Get rid of.
get rid of. I mean, there is activation there in parts of that, but maybe get rid of and for 10 and then low 10, minus 10. Probably get rid of.
Mm-hmm.
Also, are the lobes separated by hemisphere or no?
Yes. Yeah.
So there's separate ones for each hemisphere.
Right.
Okay. Well.
Yeah. So there are a lot of ROIs in this analysis. So maybe it will be worth reducing it down just so that we're not being killed with corrections for areas that we're not really interested in.
So I think we choose to, like, there are a couple of other ones that we can probably, and with the cerebellum, a lot of them you pull 1, you pull 2 because you have the lateral part and the firmest part. So
Right.
we could probably think about that a little better.
Yeah, and I was for this analysis, I didn't do any like combined ROIs, but I was thinking that would be appropriate here as well, because at least or to get rid of the ones we really don't have any. So yes, many ROIs. Actually, so to your question about the hemisphere, most of them have a right and left component, but then some of them do not. So I guess if they're more central, it might have just been,
Okay.
one.
Oh, well, yeah, I guess the vermis ones
Right.
would not have a hemisphere, mainly just the lobule.
The lobules do.
Yeah, that makes sense.
So again, speech on baseline, clear areas of activation. Past normal, we have a couple. I should have pulled out the names. We have.
Vermis Bruce 1, so I take back we should dump that one. And Vermis 10. No way. Oh well.
There's a couple more, I think. Is that low 5?
Vermis Bruce 2.
Here. This one. And purple. 5 and 6.
Those are significant?
Oh no, so none of these are significant,
Right.
but these are nearing significance. So if the Alfonso, what is the if the line is like it's not black but it's shaded darker, is that means it's like it would be significant but it's uncorrected?
Right, exactly. So it has 3 levels. If it's not showing, if it's all gray, it kind of like is not significant. If it's a little bit darker but not quite just the standard color, that's significant at the individual level, but not after the FDR correction. And the ones that are shown in full color and in black, the error bars, those are the ones that are significant across the after the PFDR correction. I'll add an option to actually specify your threshold and just like in a more clear manner for these results.
Yeah. Right.
And it dwarfs the effect sizes of there.
Yeah, all of this. Just a lot of basal ganglia. Okay, then we have stress minus normal. The cerebellum dentate nucleus was significant.
Was significant?
Yeah, so when it's the black line or black error bar here. And then there's a few. pure minus normal, the medial geniculate came up again. And then plasma is there.
So you see higher activation in a lot of the cerebellar areas on average. Also. Once you get to the right, so there's caudate, right? It goes caudate, caudate, and then all cerebellum, and then pallidum, and some phase again with thalamus. Subthalamic nucleus.
So that's it. So yeah, I haven't done any combinations here, but I can come up with a more reduced list, and Jason, I might send that to you before I run this analysis.
Yeah. It's combining the ROIs. It's
or maybe not combining, but reducing, like maybe removing some of.
We could reduce and.
I mean, there are so. Sorry, go ahead.
Go ahead, Alfonso.
We have the whole hierarchical thing approach basically to when we want to combine ROIs that we can use here as well, which is basically try to perform first the analysis on a combined larger groups of ROIs, and then for those results where we find a significance within those larger groups, then we look closer and try to break it down into smaller subregions and figure out what is happening there. And we could use basically something like that. But before we even get to that, there are other perhaps things that we should first consider, which is whether we want to look at Manai coordinate ROIs or this type of probabilistic atlases, whether we want to smooth or not, whether we want to use subject-specific ROIs. So I don't want to generate thousands of potential candidate results with different variations of everything. So I think we should try to figure out what is the one that we want to try first, and then follow that approach with respect of the ones that, I mean, another way to reduce the number of ROIs in a more data-driven manner is just to first look at which results show any activation in a speech minus baseline, for example, in any of the conditions. And then if some regions are not basically showing activation in any of those conditions, then you can remove those and focus on the regions that are speech-related in a way, basically, they show activation that is at least differentiable in any of the speech conditions versus baseline. And then we look at the difference between the several conditions and in an unbiased manner, because the first result, the way to discriminate the regions that we care about is orthogonal to the second. So we could also do something like that, basically reduce the number of regions by first performing just a simple speech minus baseline contrast and removing all of the regions that don't show up anything in there. And also with respect of the many different comparisons that we are doing across the different conditions, perhaps also we should do something a little bit more structured, which would be just running a simple F-test across whether there are any difference between the four conditions that we are looking at, and then for the results that we do find significance there, we will look at which conditions are causing that difference, rather than performing like a full set of analysis looking at the individual pairs of contrast that we care about, and then for which we will need an additional correction from performing many comparisons or something along those lines. So I don't know, but before we get to all of these details, I think the main usefulness of this first interaction would be to figure out which one are the ROIs that we want to focus on. What do you think, Jason?
That is tricky. So what would be, to make that decision, what I'd like to see are some looking at the ROIs, how they line up, see what they look like.
Yeah.
And then it would also be nice to see for a given ROI, like, so to the degree that we can compare ROIs, to just look at the responses. It'd be kind of nice to see that, and even for the speech minus baseline, but just to see. So instead of plotting it like this, where it's here's these ROIs, you're plotting it by region, and you can see. So you're plotting. So let's say we have medial geniculates in both.
Yep.
Just to see medial geniculate 4 millimeter, 6 millimeter.
Oh, I see.
Like
Yeah.
that kind of.
Yeah.
Otherwise, I don't know. certainly would want to look at how these things align to individual needs.
Right.
That's probably, I don't know. I guess maybe we could take a step back and just think about it theoretically.
Yeah.
What would be a better option?
Yeah.
I don't know.
I feel like this, as in I agree that I think we should visualize it. I do think it will take us a while to do. I don't know if it would be more appropriate for us to do it in like an individual meeting
Oh,
than
sure,
as
sure.
a group, right? You know.
Yeah, so
like,
I'm thinking we just sit down,
right.
go
yeah.
through it, and then maybe we could, in doing that, come up with like, okay, here's how we want to demonstrate this.
Yeah.
And to show at a group meeting.
Yeah. Okay, that sounds
Right. One possible way to go about that is looking at the results of the group of the voxel level analysis. You have this button that allows you to look at individual subject data for those results. So you can use the M&I space, like a group level, voxel level, volume level analysis, and display those to then project those analyses into the individual spaces and look at the anatomy of those and together with the functional activation for each individual subject of those effects, and focus on a few slices that look at the subcortical structures that we care about and figure out whether the anatomy and or the activation varies a lot spatially, basically, and that would give us a better sense of how much variability really we are talking about, both structurally and functionally, with respect of these regions that we care about, to determine whether we should move to a subject space everything, or perhaps at least for a few regions, and whether for some other structures something like an M&I space spherical ROI suffices or not, and I don't know, some basis for that.
sounds good. So that's all I have.
In the meantime, there were a couple things that popped up there that were significant.
Yeah.
So.
Yeah, I mean, even these same results, just trying the weighted probabilistic atlas to get a little bit more information, because the unweighted one, I'm not totally sure what it's doing, whether it's just taking any voxel that shows above 0 values, which might be the default, which are going to be an overestimate of the regions that we care about a little bit wider than we really care about to look at smaller effects. So I don't know, just using the weighting and using the smooth.
It's not non-zero, it's the most likely. So at every voxel, it's the region that's most likely. But I think that because we have that with this would be a perfect way for us to see, if we start to see stuff pop up. Because we're using the weight. I like that idea better than just the binary.
Right.
So we can do that. Maybe we could sit down and I can point to you where files are from TAR, some things like the individual atlas volumes.
Okay.
I think so. In order to do it, I believe what needs to be done is those individual atlases may need to be resampled into whatever template space. They're already in M&I space, so they're looking for 4 millimeter.
Okay.
Right to those volumes.
So then, what was our decision about smoothing? So should I rerun the analysis with a 4 millimeter?
If we're going to focus on the probabilistic atlas, then we don't need any smoothing. The probabilistic nature of the atlas itself effectively takes that into account, right? Because it's supposed to already capture the variability across subjects in the spatial location of those regions. So that is effectively the smoothing. So unsmooth data and probabilistic atlas is probably fine. If we are going to look at the M&I coordinate stuff, then I would probably smooth the data, because M&I, for at least many of those regions, those M&I spheres might be a little bit too small, and smoothing helps make them bigger, and also they might be varied in their location across subjects, so smoothing also helps in making it a little bit more robust.
Given we're on the 4 millimeter smoothing, when you say with probabilistic atlas, the distinction here is if you're using the weighted method, then that would take care of what you.
Right, exactly. I'm talking about the weighted nature of those. If we are thresholding those, we will still need to smooth to to basically effectively unthreshold them and convert them to a reasonable leveling of values.
Okay, so I'll do that before we choose.
Just sort of jumping onto that, just a quick question. So I've been running for the rhythm study for the cortical ROIs. I've been running it with unsmoothed data, but this is supposed to be group. Like this is just group level, so not individual ROIs. Should I try smoothing it a little bit? Just because
what is the nature of the ROIs that you're using?
So the ROIs are the speech lab ROIs, but they're not individualized. They're just the group.
But are speech ROIs put into M&I space or are speech ROIs on the surface?
It's on the surface.
So then we don't need to smooth it because the surface data is already like a very good representation of the cortical region. I don't know, and the regions are relatively large already, so the smoothing wouldn't change much in any way. What do you think, Jason?
I don't know. I guess we need to. I don't know. It seems like we need to like get some more concrete notions of when to smooth or not. Because yeah, I mean, I think in the past we wouldn't smooth. We'd extract the data from each individual. We wouldn't smooth, but then we would smooth along the surface. No, actually, I take it back for the ROIs. We probably don't need to smooth. But if we were going to smooth, then what we'd want to do is smooth along the surface, not
right
in the volume.
Right.
So
I mean, typically for ROIs, we don't smooth unless they are defined in a way that, so smoothing is basically effectively kind of smoothing the ROI definition. So it takes something that is like a binary mask and converts it into a probability distribution by smoothing, taking into account the variability in space that the smoothing kernel effectively represents, right? So it takes something that is a binary mask and smooths it and makes it some Gaussian distribution-like thing by leveling off the boundaries and makes it into a probabilistic map, and then you apply that probabilistic map. So it makes sense to smooth when you are not certain that when the region is relatively small, so that variability across space makes some sense. But it doesn't make too much sense to smooth if the region is relatively large and you already have the boundaries well defined, even on whatever space, whether it's FS average in this case or M&I space.
The only reason that I would think that it would be necessary is if you're trying to account for some amount of like spatial variability in, like if that region, well.
Right. So there are a few regions that we get that are fairly small that are very, very difficult for free surfer. So way back when we would go in and manually correct all of these, but now we're working on a scale where that's maybe not feasible. So in that case, so for some inferior frontal gyrus regions, they're small enough that maybe some smooth. Like I could be talked into smoothing for those basically.
But perhaps we could create like a probabilistic atlas definition for speech ROIs where we smooth the regions that we think that maybe actually effectively benefit from that smoothing, because we think that the variability in the spatial location is large, and not smooth the regions that we think are already well defined, especially by free surface normalization, and just create our own probabilistic atlas of speech-related ROIs in FS average space. So we won't have to think about whether to smooth globally all of the data or not later on. What do you think?
Possible, sure. Yeah. I mean, that may be worth thinking about. It's part of our reason for giving up on the time it takes to correct these was that we did this sort of we did an internal study to show and found that correcting them didn't really change a whole lot, but that was sort of kind of limited, and it does change some, right? So that may be where we want to start, Alfonso. Maybe expand a bit before we spend any time.
Right, and the thing is that it happens on only a few regions, right? Not all of them. So some regions are very consistent across subjects in average space, and some regions are not all that great. So in order to be able to discriminate between those, what is happening across different regions, we, rather than decide whether we want to smooth the whole data or not before applying our level analysis, perhaps we can just consider whether we want to have like a smooth representation of our ROIs themselves. So we can actually smooth the ROIs that we think need smoothing, and not smooth the ROIs that we think are fine as they are.
Okay. Cool. I think for right now, based on this conversation, it seems like I won't smooth. I'll use the
Right.
data.
This is like always. So if you let Jason and me decide things, the answer is always wait until we figure this out. But yeah, right now, tone smoothing is probably the best solution.
Okay. Sounds good.
I'm sorry about that.
Can I just quickly ask like a general question about S rate, like not ROI specific, but I'm just curious. Like, so the Godiva model postulates that the SMA is involved in the execution of articulatory timing. Like, so and between all the speaking rate conditions, you don't see anything.
So it's not just a timing thing though. It's like in terms of the experimental conditions. So so we're not just we didn't just, well, not that I was part of it, but when they ran the study, they didn't just ask them to speak faster or speak slower. It was more like we're thinking about it more on like a speed accuracy continuum. So yes, the fast condition is fast, but they may be compromising, the accuracy of which they're producing the sentences. Whereas in the clear condition, there's a real emphasis on just how clearly they're enunciating, and similarly in the stress condition. So it's not just, we don't think it's a rate, even though we're calling it the S rate study, it may not be just rate, but also how you're chunking the syllables, and how you might be reducing them in the fast condition, but they're more likely to be more distinct in the
Are you
go ahead, Saul.
Sorry, are you comparing error rates across conditions? Like, is that a behavioral measure that you're looking at?
I haven't. I can definitely pull it. I feel like it was pulled before, but I don't. As in, I haven't because I removed those trials, for example.
Oh, right. That makes sense. Yeah.
I would need to double check what, had those summaries come out, but I don't necessarily think that they were making more errors because, the sentences weren't, constructed in such a way that we would expect lots of errors. They're not, they weren't like tongue twisters or like non-native sounds or anything. And young adults, so I don't think we would expect to see anything interesting.
Yeah, sorry, just curious.
But they were.
It might be interesting to see if that is like the idea, that it would be, clear is more, the attempt would be to make it more accurate and fast. I don't know.
Right.
Anyway. Yeah. This is probably irrelevant to.
Well, the other thing I was wondering about is whether like activation differences might emerge in like more like prefrontal executive function areas, because like, I mean, if you like in typical conversational interactions, like we're dynamically adjusting how we speak all the time, and that's because you're constantly like anticipating the perceptual needs of the listener and making decisions about like how should I like modulate how I produce this, like what acoustic cues should I produce and stuff. Like, do you think?
Yeah.
Like, I don't know. Like,
right.
Maybe like within the speech network itself, it won't modulate that much. But if you look like more.
Yeah, and I would need to, like, to be honest, I would need to refresh my memory exactly what we found at the cortical level. I don't remember all that.
I'm just curious. Yeah.
And in terms of this analysis, do we have actually some type of a priori hypothesis about which regions we actually expect this type of difference to show up, or we are doing a little bit more of an exploratory thing to see what comes up across the entire brain and then see what that makes sense in terms of our models?
It's been more exploratory so far, but I think we do have some hypotheses.
We do have some. I know that part of it is expecting that you have you may have greater auditory activation during the clear, when you're trying to really do a good job, and then maybe more right hemisphere.
Like you're monitoring it more
Yeah,
closely.
you're monitoring it. Where with the fast, the idea is that maybe what you're doing is so for the clear, you're reducing the target size, so you'd end up with more error signal, and that might be part of what drives it. And you're relying more on feedback.
Online correction.
That's interesting.
But I know that there was, I believe that there was also a P4 piece to it too. I don't remember where, if we had come up with some area that we thought would be more or less active from a planning standpoint.
Right.
I don't remember. We can dig that out.
Yep.
Sorry, I didn't mean to get off the topic of ROIs. Should I go ahead?
Yeah, I think we're ready to look at the loss stuff.
Okay. So I reran the speech minus baseline contrast with like the updated and it doesn't look very different to my eye anyway, but
Right. So the overall thing, the issue before was that we were seeing this type of discrepancy in the apparent position of the mask itself and the regions. So select the one that says effects in there, and then right at the bottom it says raw, something about raw. In the window that you're showing in the up left, it says effects. And in the almost the last one, it says raw data display. This is just to avoid reduce the smoothing thing that is happening at the borders, basically. So what is happening there is that well, I don't remember the name. What are the name of those ventricles? The anterior ventricles, Jason?
Lateral ventricles.
Lateral ventricles. So the actual position of those ventricles across the subjects varies. The size and the position varies a little bit even after M&A normalization, and we are running first level analysis that actually perform masking to determine which ones are in brain voxels versus outside of the brain voxels. And the thing that was happening is that for a few subjects, some of the voxels that in this template look like coded, they were just within the ventricles themselves, so they were masked out because they didn't have they were identified as out of brain voxels. And then when the second level analysis came in, if it found a voxel that had been masked out for at least one subject, it removed those voxels from the analysis. So that was why we were getting all of this cropping at the borders, and the same thing happened in the cerebellum. The cerebellar position, basically in the inferior portion of it, was varying across subjects. Some subjects were a little higher and lower, and a little anterior and posterior, again, in where the exact border of the cerebellum was, even after MRI normalization, and that basically made the mask that the second level analysis used across all subjects to be like an intersection mask of all of the masks where the brain was expected to be in every individual subject, and that was a very conservative mask. So everything that was at the border of the region that for at least one subject had been considered outside of the brain had been removed. And this is what I basically changed for the software itself to actually run this analysis, which forces the analysis to be run on every individual voxel unless all of the voxels, all of the subjects in that particular voxel have been identified as out of brain. So instead of using the criteria, the rather conservative criteria of if one particular subject had identified that voxel as an out of brain, then remove that voxel, it was using the now extremely liberal criteria of, well, if a voxel had been identified in at least one subject as inside of the brain, then still include that voxel in the second level results. So now it's a more liberal mask, and it doesn't include any sort of masking. But this effectively tells us that there is
this one here.
This is exact same mask. I only changed the actual software itself so that when you run the second level analysis, it doesn't do this implicit masking. It just uses a more liberal form of masking.
Okay.
So I'm talking about two sorts of masking. You can mask your analysis by the explicit mask that you give as a file, but then in addition to that, there is also what is called an implicit masking that is just part of the analysis themselves. And implicit masking happens at two levels. Happens at the first level analysis results when you're computing analysis for every individual subject, and also at the second level analysis results when you're computing analysis across multiple subjects. And this implicit masking basically tries to not run analysis in uninteresting voxels. So within subjects, that is voxels that are outside of the brain for that subject, and across subjects for second level analysis that happens in voxels where originally happened for any voxel that had been considered as outside of the brain for any one particular subject that would be removed, and now it doesn't happen. It basically only for those voxels that have been considered outside of the brain for every individual subject, then those are masked out as part of the implicit masking. So there are two masks, the explicit and implicit. The explicit is the one that you specify in that file, and the implicit just happens always. It's just a way to remove uninteresting voxels from the analysis themselves.
So you're saying that I need to rerun the first and second level with this one?
No, the first I left it. I don't know. I wanted to run this by you. What do you guys think? The fact that all first level analysis use this implicit masking and is determined by an 80% value of the global signal. This happens by default in SPM. So it's happening pretty much across all analyses that have been run in SPM. They use that sort of implicit masking in first level analysis. So I use the default settings in that. I'm still using this 0.8 value. I don't know. In some particular cases, that might not be a good solution, but it's rather strange. I mean, it happens, for example, if you're using a experimental coil that gives you a very high signal-to-noise ratio in the borders of the brain compared to the center of the brain, and sometimes you get this masking that removes portions of the center of the brain. That's because the scanner itself didn't have much sensitivity, and it gives you lower average ball signal values within those regions. So those are a little bit more of corner cases. In general, this 80% of the global signal threshold that SPM uses works relatively well, and we can actually look at first level. If you want to look at this in more detail, we can look at the first level results for some of this data to look at. Actually, why don't we do that briefly? Could you go into the other window, the one that's the second level results window, the main, yeah, that window, and click on the plot subjects stuff. So the one that has multiple faces, yeah, that one. And now let's see which one might be a little bit more interesting here. Let's look at we want to look at the net. Well, just select just the first, that option.
Cuttings will suffer because of where it is.
Let me see, this is going to look at the anatomy. Well, we don't care about the anatomy in this so much. Okay, so select all subjects and then just click. I don't remember the range of numbers that we're seeing here, but perhaps, yeah, increase the value to, well, we can do that later. That's fine. Just click OK there. We probably need to change the threshold to see something a little bit more meaningful.
You're smoothing over within and ventricle.
Okay, so and again, select the effects and plot the raw just to remove any issues with that. Right. Okay. So now you in the slide that I showed at the bottom right, you can move across subjects, and this is the activation for every individual subject of the. We're looking at a speech minus baseline here, right?
Correct. Yes.
Okay. So and anything that doesn't show, if you lower the threshold is the one that says 0.25, is the top right slider. If you put it to 0, something like that, you should see pretty much all brain. Except the regions that anything that is in black are the regions that has been masked out because they are considered outside of the brain. And if you move across subjects using something like that, you will see that the actual location of those regions are slightly varied, particularly if you see, well, yeah, that is not exactly the same regions, right? So there are some voxels that appear to be outside of the brain in one particular voxel and not others.
Well, so if you set it at 0, what's black is it masked out, or blue?
Black.
That's right. You can, let me see. Yeah, you can change the raw to a smooth stuff so that we actually see the background in there. it's fine. We will see the boundaries to give us the information that we want. So clicking again on effects and change the last option from raw to smoother display, just so that we actually see the in cases, yeah, and then just move across subjects. So that's kind of like this boundary that you see in black is the actual within subject mask that has been used. If you lower the slider that is just the anatomical slide to look at the more inferior portions where we were talking about the cerebral stuff. So if you click down to look at, I don't know, my coordinates -20 or -30 or something like that, to look at.
More. Is that?
I'm not sure what we want to look for. So there I see something that looks like lines around what would be ventricle.
Mm-hmm.
But can we just quickly
Right, just a slightly higher value, so yes, well, that's fine. I mean, that should show you still the mask.
Should these be masked? Should these be, because wasn't this the analysis was run on with the subcortical mask?
Correct.
Right, but the mask is applied at the second level, so here I don't believe
right.
we are looking at everything basically.
Right.
And this is mostly the idea here is just to show the level of, well, if we don't have any sort of like at this threshold level, we are just looking at the functional. We are not looking at the. So we're looking at the level of the functional, well, variability in the location of the brain if there are, even after MNI normalization, and things like the ventricles and things like and the borders of the brain show a little bit of variability, because even though on average the boundaries at the boundary location, that doesn't mean that exactly for every subject it will be exactly at the same location. So there are some subjects that are going to be a little bit further up and further down.
Can you go up so we see ventricle? A little bit more. Okay, so right here, when we put the overlay on, will we expect to see some? Here, just stop it there. A few overlay. We're expecting that.
Right, and now move across subjects, and you should see that the actual position of those ventricles is different. And sometimes it over. Well, in this case, you need to click the raw, because otherwise the regions that are shown there. So select raw, and now increase the threshold just to remove regions that, so we should be able to see it in there.
So right now we don't see it. What would we need to do to see it? So I'm not seeing anything that indicates. I see lower activation, but I don't see something like explicitly removing the voxels.
Let me see, how can we see that easily?
But in the raw data, why would that be? Why would the raw data be different? Why would there be?
Well, because the raw data has been masked already, so there is an implicit mask that is acting upon the raw data, and it's removing regions that are considered outside of the brain. And let me just browse through the data. Let me see if I can decontrol the screen for a second and browse through the data quickly to show you what I mean there. Yeah. Okay, so let's see. So something like this. Okay. Now.
It's one there where it's
Oops. Sorry, the delays.
Venture capital.
So you can type out your paper.
Yeah.
Yeah.
And then yeah, I'm not seeing it either. I could find it in the original masks, but I cannot find it in here just by visual browsing for it. So I don't know. Perhaps it's simpler to look at the anatomy and see how can we look at that in a simple manner. Because by default, it's not going to show us the anatomy very well. Let's see if I can see it in this place. Okay, so this is a little bit exaggerated, right? Because I'm not finding the subtle thing easily displayed. But if you look at this brains basically across subjects at these very inferior portions, and we are looking at a portion of the cerebellum, also a portion of the more anterior temporal lobes, and the eyes are the bright things in there. You see that the portion, the thing that you see in black here are all of the things that have been masked out at the individual subject level, so regions that are considered to be outside of the brain. And that is not exactly the same region across all subjects, right? If you look at the border where that particular voxel is, then sometimes that is going to be inside of the brain and sometimes that is going to be outside of the brain. And this masking is happening at the level of individual subject data. So we don't even estimate, try to estimate the speech minus baseline effect at this voxel because we know that it's outside of the brain and it's going to give us just some noise. So why we were even estimate it. So at the first level analysis, we remove those voxels from consideration. And the issue is what's happening with those voxels at the second level analysis. So you want to include a voxel that might have been considered outside of the brain for one particular subject, but has the information that was inside of the brain for the rest of the subjects, so you want to remove that subject. Does that make sense?
That makes sense. I'm curious about how it deals with the ventricles, though, because it doesn't look like they're maxed out.
Right. Let me see if we can find it then. Perhaps I can use that. The problem is that something that is masked out appears in black, and something that is, sorry, not that. Something that is in the ventricles appear in black as well, or in transparent if we decide not to show it at all. So that makes it a little bit more complicated.
That one, if you go back to,
Sorry.
That's probably one more. What's right there? Oh,
that one too.
The next one. It was that one. That really bright spot. If you take the view, the overlay, take that off. It's mostly ventricle, right? For that subject.
Yeah. That's because I'm showing me do this. Perhaps I can do this too. Okay. I think. Can I change the color? I think I can. Let me try this 1 second.
So what are these outlines?
So these are the borders. I mean, it's a technical thing. These are the borders between the regions. I cannot put a zero value in here that I would like. These are the borders between the regions that are above this threshold value and below, and the color indicates whether they are into negative or into positive values. So it's so they are very close because I cannot get this to exactly be zero. They are not exactly the mask, but they are as close as I can get it to that value. To be in the actual mask, the border of the regions that have zero values, not numbers, those are the ones that are outside of the brain, and the regions that are within those masks are the regions that are within the brain. And if I look at the actual values, it should look like, let's see. Then we should, I should use a different color for that. Let's use jet. Well, but in this case, they are not all outside of the mask. Yeah, I'm trying to see the regions that are. Not in here. I cannot see it with these plots. I'll look at this later on my time and show you what I meant with the ventricles in there. I was basically looking at the actual subject-specific masks which are generated. So when you run second-level analysis, you get within the folder of your second-level results, which are this folder. You get a file that is called mask.nie that contains the actual mask that has been used across the entire brain, and which is a combination of whatever explicit mask you use and the implicit masking that the second level analysis actually specified for the voxels that are removed from consideration. And the implicit masking is basically this type of intersection of all of the individual subject masking. Any voxel that has not a number for a voxel across at least one subject is being removed. And what I was seeing with those masks when running the original analysis that the original version of the software was that those masks were actually removing some portions of the ventricles as long, in addition to the borders of the cerebellum. But I cannot see it in these displays that I'm showing you. So I'll just try to figure out which particular subject was giving me was causing this original mask to be the way that they were, and then I'll look at the data for that individual subject to see how that happened. But I cannot see it from these plots anyway. So sorry about this break then. So can you, Matt, do you want to continue then showing us those results? I'll let you take over the screen then.
I mean, that's basically
right. The results now should be very similar to what they were before. They only should be a little bit more inclusive. So instead of just cropping some portions of the brain, you should see some results. Only that the results that you're looking at those voxels, because the regions that were being cropped were the regions where at least one subject, but it could be more than one subject, has been considered outside of the brain. And since we are not running the first level analysis to remove that masking is still there. So it's only that they are now considered to have a zero effect for those individual subjects. So if a subject in the region that we care about of the brain was considered to be outside of the brain, now for the second level analysis is assumed to have basically a zero value of the effect size for that subject. So that reduces the chance of finding any significant effect for that voxel, but it doesn't totally kill it as the implicit masking used to do. So in short, the results should be relatively similar, but you should see a little bit larger regions than what you were seeing before, regions that get a little bit more into the correct and the borders of the cerebellum.
Thank you.
No problem.
I didn't proceed to look at any of the other contrast with the subcortical mask until I was
Sure. I think if we could have these meetings be in the hour, 20-minute range, that would be more tolerable anyway. But so yeah, we have a few other things to look at, and I got a new task tacked on late last week that I'm chugging through, and when that's done, I believe that when we're not meeting, I can really work on the ROI stuff, devote some time to it. It's this really annoying thing where we flip-flopped a couple of times about how we want to do the abbreviations of the ROIs. This comes up, Saul, because so they're a figure. So if you have a figure, even on the website, you can grab a figure. I'll try to track that down, but I noticed our abbreviations kind of flip where sometimes the gyrus is capitalized, sometimes it's not. And
isn't there something else about it? Isn't it sometimes gyrus and sometimes cortex?
That's on purpose.
Okay.
Now it may flip the time. So some so there are some areas of some ROIs that don't just cover a gyrus or a portion of a gyrus, just an area.
Mm-hmm.
So just kind of.
But one is used in the labeling, in the figures, and one is used in
that we don't.
The annotation.
The same area should be used the same way. The annotation's tricky because that's why in that file I have, here's what it is in the annotation, here's what it is, how we refer to it. Mm-hmm. And that's because going back, so if we change the annotation, then there might be some a mismatch. We'd have to go back and change all the associated color tables.
Right. Yeah.
So there'd be a mismatch.
And I'm sure there are multiple scripts that have used it in one
way. Right. But it might be worth, we could just draw a line in the sand and see how it goes. And if it's a problem. Because it's a pain. That part of it is a pain.
Well, we do have the matching document.
Right. But it would be good to have something that's up to date. So I'll get to the point of that once and for all.
So I had two more questions.
Sure.
I don't know. Sorry, I don't know if.
No, that sounds good. I thought we were wrapping up. I was about to hit stop on the recording, but if you got questions, we'll keep.
Oh yeah. So the first one was Alfonso. We had talked at one point about coming up with a way to specify specific ROIs within an atlas, and that which might be useful for if we have a priori hypotheses that we want to correct for only those 10 ROIs, then it would be good to have a way to specify those so that when you do that ROI analysis, you actually get the FDR correction that you want, or the correction that you want.
Right. So yes, that functionality is in there. I still haven't plugged a way to specify because I'm still struggling out to what is the best way to specify all of these options. So currently, so I'm just adding options to the FL command syntax in the case of the ROIs, but I don't like that, because that doesn't happen for the rest of the FL commands. Basically, everything is provided through these config files, and in the FL command, specifically, you only typically just say which particular analysis and which particular pipeline you want to run. So I don't want to end up having too much information being added from the command syntax and the FL command in practice, because I think that is, then you're not going to remember exactly how you run that command. So I think it's best to put that into configuration files. But I don't know. What do you guys think about how to enter that information? Because configuration files, on the other hand, at least for second level analysis, they should be relatively independent, or at least it would be best if they are independent of whether you are running them at the ROI level or at the voxel level, right? Because you are only specifying the information across for the second level analysis itself, not so much the details. So that speaks against putting into the configuration file. On the other hand, for all of the other reasons I just said, that speaks against putting in the command line itself. So what do you guys have?
Would you have an ROI config file that's separate to your second level?
To create like an ROI specific configuration second level for would you make that different from the standard second level analysis, or it would be just inclusive? It would contain also the second level analysis definition, or would you have like a...
I would think it's because we're using the same, at least as far as I know, the use case is that we're using the same second level analysis for the ROI.
Sure.
So I think that could be separate, but the kinds of things that you put in the ROI config file is pointers to the, whatever the volume files, or if you have to specify specific indices, if it's an atlas, or if there's some, like Saul said, like for some set of ROIs, they might be, hypothesis driven, you want to correct for them, but maybe a second set is exploratory. So those kinds of things.
Right, that's a good idea.
A fair amount of sense to have the ROI building on that, the ROI configuration file point to the second level analysis file. That way, you can have, I ran the second level analyses and now I'm interested in them, but ROI based.
Exactly. Yeah, that's a good idea. You're not duplicating.
Yeah, and it's just very clear the logic.
Yeah.
The logic.
Right. And what about subject-specific ROIs? Would you put it in there? And the thing against putting it in here is that it doesn't make very clear the association between each individual subject and each individual subject-specific files. We could, for example, put it into the TSV files, the participants information file, because in that we always have a line that says the subject ID, and then we add information about that subject. Although having file names in there doesn't make that much sense, because we are using that file for specifying second-level covariates. So what do you think about that?
Could you add it to the subject config file, like that original?
Right, we could add it to the subject configuration file where you add like ROIs, but how would be, yes,
Is there a reason that you need to specify different ROIs for different subjects?
Only for subject-specific analysis, right? When we want to do like a subject-specific ROI definitions, we can, like, for example, for a freezer for parcellations, things like that.
Well, I would assume that there would be some naming convention where you'd have the same name for the same ROI that you'd be wanting to compare from different subjects, and so you would just specify that name.
Right, but currently the ROIs are not stored in any like consistent way. That would make sense if we are putting the ROIs into our own whole folder structure, but currently the ROIs are taken from wherever we want in different places. So it's difficult to kind of create an association between individual subjects and ROIs unless we put those ROIs within those folders directly.
We could do that, right? So I thought we were going to not within the FL pipeline folder. Well, no, I think it is. Sorry. We talked about some way of having the FreeSurfer Recon directory being at least in a standard location, and then if we had something where really it's pointers to those, the location is going to be different for each subject, but it'll be consistent. So if you have pointers to I want to access the APARC plus ASEG, with a specific name, that's what it's going to be. And then with the other ROIs, when you generate them, we just generate them. But those are just template, right? So it seems like we can maybe we could at least formalize where these things should be stored. But then another piece of it is actually indicating which ROIs you want to use in your ROI analysis.
Right.
I think that's what will go into the config file.
And so you want, right.
So
go ahead.
So at least with the speech lab, like the not individual level ROIs, there's like a header file that has the name of each ROI that you use, that when you pull up Rex, it gives that name that it's associated with the ROI. So if you were to specify just the name that's in the header file, you'd have to know what the names are in that header file, but
right,
and what they correspond to.
Okay, so I could offer like a list option that lists you the names of an ROI if you just specify the name of the ROI, so that you can see what those names are, and then you can specify just the individual sub ROIs within an atlas file by those names, and that would make sense, I think.
Yeah, I think that.
Okay, that's reasonable. And I think for now, probably then I'll just use this idea of using ROI configuration files and allow people to specify even subject-specific ROIs in that way, just giving something like a combination of subject ID, so something like SIG PDS 01 C03, and then comma, and then the file name, and allow to do that basically for subject-specific ROIs or for standard ROIs that wouldn't have the subject-specific comma at the beginning or something along those lines. And then if we end up having the ROIs located in a specific location because within the part of our folder structure, then I will add additional functionality to take that into account to simplify the way that we specify individual ROIs and regions. But for now, at least, I'll just give you guys the option within these ROI configuration files to specify all of that information, including subject-specific ROIs as well, even though that may be a little bit cumbersome in general. Sounds good?
Yep. And then the last question I had, which is probably more simple. So Elaine has code for creating, or she was using the con script to make the MNI space spherical ROIs. Is there an equivalent command for making a circular ROI on the surface?
I don't know of that. Jason, do you know of like some FSL commands or something, or free surface commands themselves that might be able to generate that?
I'm not aware of them, but that seems like.
I mean, that's a good point.
Saul, have you Googled that at all?
No, I haven't. I figured I can. I just assumed. I thought that maybe this was something that somebody has, but if not, then.
Right. I mean, I don't have any con or SPM command to do that. I mean, it's a little tricky because the free surfer coordinates are their own walls, right? So if I what do you mean by distance exactly in that space? So. But it's doable. I mean, there are reasonable notions of distance, like just stepwise through the number of edges, for example, in the tessellation. That makes sense. Or geodesic distances, or things like that to define a region. But I don't know of any software that would do that basically automatically. One way to do that pseudo automatically would be if you create an ROI that has one single voxel light up, and that voxel is at the correct coordinates in FSL.
Oh, yeah.
And then you just smooth it and smooth it and smooth it. Then threshold that smoothing map by some height level. Effectively, you are kind of like doing the same, right? So.
Right, that's true.
But again, it needs a little bit of manual labor, and also I cannot tell you any way to a priori specify create that individual free surfer ROI with a given coordinate being 1, so being 0. Let's see, how can you create that file? There is that functionality of how to associate one coordinate with one voxel in the surface is part of the surf show stuff, because you can project voxels into the surface, but it's not basically made into the exterior as a function to create a file. It doesn't allow you to basically create a file that what you want. So I don't know. I'll think about it. If some easy solution comes up, I'll let you know. Otherwise, try googling it whether there is perhaps FreeSurfer has something like that. Either the whole spherical ROI, or just at least a way of specifying creating a file that has one voxel one particular vertex being 1 and everything else being 0. But
Okay. And it might make sense. I mean, the reason I was doing this was, or I was thinking about this was because if there was some, like in the meta-analysis of stuttering, like stuttered speech compared to areas that are greater in stuttered speech compared to, or people who stutter than people who don't stutter. I guess they do it in M&I coordinates anyway, so maybe it would make more sense to do that. I was just thinking if we had a spot on the surface that we say like, oh, this is the maximal activation area, perhaps associated with an M&I coordinate, then if just to do a
coordinates all then projected to the surface, like do some kind of transformation that way.
But there is a free surfer
Yeah.
within has this mapping.
Yeah.
From M&I coordinate to a spot on the surface. And I thought I had a lead here. And I may have it as soon as I'm not looking it up on my phone.
Well, maybe this is not like of the utmost importance now, so maybe we can, put this off to a later time or another conversation.
Sure, no problem. It's a good point. I mean, if there is nothing in there that allows us to this is functionality that would be useful to have, so I'll put it into my queue of stuff to add, and I'll just create a function similar to the one that we have for creating spherical ROIs within the M&I space to do the same, or at least to have the option to do that in FS average space as well.
All right, awesome, thanks.
No problem. Any other questions or issues before we leave? I need to take off pretty much now already.
I think we're good for now. Do we want to set another time?
Sure, excellent. Do you want to do next week? Which day do you prefer?